Question first. Name any two figures that have both line symmetry and rotational symmetry. The two figures that have both line symmetry and rotational symmetry can be circle and square. If we see for circle, for rotational symmetry, consider this dot as a reference point. When you rotate it 360 degrees, that is, we have to make complete rotation. Reference point is here after rotation, and still this circle appears to be like original one. Again, we rotate it and point comes here. Again, it appears like original one. Therefore, it satisfies rotational symmetry. Again, line symmetry. What is line symmetry? That is, if you put your mirror on these lines, you will be able to see this portion on mirror, which will ultimately appear like the original one. Therefore, circle is one object that has both line symmetry and rotational symmetry. For square, for rotational symmetry, let's consider a point P here. When you rotate it 90 degrees, P comes here. Still this image appears like original one. Again, you rotate it, P comes here. We are rotating it clockwise. Again, this image appears like initial one. Then again, rotating, P comes here, clockwise direction. This image is similar to original one, and so on. Thus, square has rotational symmetry. For line symmetry, if you place your mirror here, on mirror you will be able to see this portion exactly like the original one. Therefore, square has both line symmetry and rotational symmetry. Well, you have already studied it numerous times before. This is just a repetition. That is first. Second, draw wherever possible a rough sketch of from 1 to 4. So first is a triangle with both line and rotational symmetries of order more than 1. Well, we have studied this. Equilateral triangle follows this criteria. That is, it has 3 line of symmetries that are same as its median. And what is a median? A line drawn from any one vertex to its opposite side, that is opposite side with middle point. So it has 3 line of symmetries. And for rotational symmetry, it has again 3 rotational symmetries, because this point rotates in 3 directions, and in each direction the image is very similar to original one. Therefore, equilateral triangle has both line symmetry and rotational symmetry with order more than 1. Second, a triangle with only line symmetry and no rotational symmetry of order more than 1. Well, we have studied this as well. An isosceles triangle has only single line of symmetry and no rotational symmetry more than 1, because one order of rotational symmetry is with every object on this world. That's second. Then a quadrilateral, a 4-sided closed figure with the rotational symmetry of order more than 1 but not a line symmetry. Well, it is not possible. Any object which has its rotational symmetry will always have a line symmetry. So therefore, not possible. That's third. Then a quadrilateral with line symmetry but not a rotational symmetry of order more than 1. It is opposite of this statement. So we have isosceles trapezoid, which has a line symmetry, that is single in this case, but no rotational symmetry. That is, if we rotate it, we will not have rotational symmetry more than 1. So you can get an idea from both these statements that you can have an object with a line symmetry but not a rotational symmetry more than 1. However, its opposite will never be true. That is, if a quadrilateral has rotational symmetry, it will always have line symmetry. So what is an isosceles trapezoid? Isosceles trapezoid. First of all, let's understand what is a trapezoid. A trapezoid is a quadrilateral with exactly one pair of parallel sides. So in this case, these two sides make pair of parallel sides, and these are not parallel. In a trapezoid, the parallel sides are called bases. These are bases. So we have two bases. A pair of angles that share a base as a common side are called pair of base angles. So these will be your pair of base angles. Similarly, if you will take this as your reference, then they will be your base angles. A trapezoid with the two non-parallel sides, the same length, is called isosceles trapezoid. That is, the length of this and this side, that is non-parallel side, if they are equal, then the trapezoid is said to be isosceles trapezoid, and in that case only we will have a line symmetry. But again, this isosceles trapezoid will never have rotational symmetry of order more than 1. So that is second. Question third. If a figure has 2 or more lines of symmetry, should it have rotational symmetry of order more than 1? This question is just a repetition of one of the statements from the previous question. That is, if a figure has 2 or more lines of symmetry, so we will take some example, then we have to show, or should it have a rotational symmetry of order more than 1? Well, yes. If a figure has 2 or more lines of symmetry, it will certainly have a rotational symmetry more than 1, because 1 is by default with every object in this universe. So let's give a reason. What is this? This figure is a heptagon. It has 7 sides, 1, 2, 3, 4, 5, 6, 7. So from a regular polygon perspective, every regular polygon has lines of symmetry equal to its sides. So it will have 1, 2, 3, 4, 5, 6, 7 lines of symmetry, and those lines of symmetry will create an angle of 51 and 3/7 degrees. That is, each angle will be of this value, because when you divide 360 by 7, you get 51 and 3/7 degrees. Therefore, more lines of symmetry makes more internal angles, therefore making more ordered rotational symmetry figure. For example, in heptagon, lines of symmetry creates each internal angle this much, which makes order 7 rotational symmetry possible for heptagon. Therefore, if you take a point here, you rotate it, this point will come here, and this image will still look like initial one. Again, here, here, here. So 1, 2, 3, 4, 5, 6, and 7. So we will have 7 rotational symmetry, and it's true for other regular polygons as well. In general, we can say not only for polygons, but for any image or any figure which has 2 or more lines of symmetry, it will certainly have rotational symmetry more than 1. So that is third. Question 4. Fill in the blanks. We have shape, center of rotation, order of rotation, and we have to find angle of rotation as well. Same questions are repeating, just their way of representation is changing. So we have 4 columns: shape, center of rotation, order of rotation, angle of rotation. So these 3 criteria are always important when we study symmetry, and we have to fill up those only. So if you take a square, we have to find center of rotation. And what is the center of rotation? That point, that fixed point along which your figure rotates 360 degrees. So in case of square, we have diagonals. What are diagonals? That is connecting opposite vertices. So wherever they intersect, that will be your center of rotation. That is, you put your pin here and you rotate the object. So that is diagonals, intersection point. Now order of rotation, well, we have studied it several times, that it is a regular polygon having 4 equal sides. It will have 4 order of rotation. Take it a reference. Moving here will create 1 order, 2nd order, 3rd order, and 4th order. And angle of rotation is obviously 90 degrees. That is, when we rotate this square along this fixed center O 90 degrees, we will get this square back. Now for rectangle, diagonals, intersection point, again we construct diagonals, and wherever they meet, that is our center of rotation. And order of rotation, obviously it has 2. Take it as the reference point, rotate it 90 degrees, it will be like this. But this is not equal to this, so we'll have to again rotate it 90 degrees. Then we'll have this point here, and it will appear like original rectangle. So that will be order number 1. So you haven't rotated it 90 degrees in order to get to this image. You rotated it 2 times 90 degrees. Therefore 180 degree is your angle of rotation in this case. And again, when you rotate it 180 degrees, you get this back. Therefore we have order of rotation as 2. So we are just repeating the previous questions. Now rhombus. Now first of all, what is a rhombus? Again, it's a revision. It's a 4-sided flat shape. That is, it is a quadrilateral with straight sides where all the sides have equal length. So here we have a rhombus, all are straight sides and all are equal in length. Also opposite sides are parallel, so these are opposite sides, they make a pair and they are parallel. Again, make a pair and they are parallel. Also opposite angles are equal. So this angle will be equal to this angle will be equal to this angle. Therefore it is a rhombus. Center of rotation will be its diagonals. This will be your center of rotation, and the angle at which you rotate in order to check order of rotation will be again 180 degrees. Because take a reference point here. You rotate it 90 degree, this will come here, but that will not appear similar to this image because that will be like this, which is not similar to this one. But again, when you rotate it 90 degrees, this point will come here and it will appear like this. So 180 degrees is same as we have for rectangle, and order of rotation is 2. Equilateral triangle, we have just studied about it in previous question. So this is your equilateral triangle. It has median as your center of rotation and it has 3 order of rotation, and you have to rotate it 120 degrees because we have 3 medians in this case, gives you 360, therefore 120 degree is your angle of rotation. Again, to simplify it further, this angle is 120 degrees. Again, this angle will be 120 degree and this angle will be 120 degrees. Now regular hexagon, again what is regular means? When sides are equal and angles are equal as well. Hexagon means 6 sides. Again, diagonal intersection point will be your center of rotation, therefore these are diagonals, wherever they meet that is your center of rotation. And regular hexagon has 6 sides, so it will have order of rotation as 6 and each angle will be 60 degrees. And how to find this angle? Simple, angle at a point is 360 and divided with sides. So 360 over 6 gives you 60 degrees because 60 into 6 gives you 360 degrees. Circle, well, it is the only figure in this world which is order of rotation as infinite. Also sphere is, it is just a 3-dimensional object of circle, and center of circle is very well known to you. That's center of circle, and angle of rotation is any. Even if you just rotate it with 0.1 degrees, 0.001 degrees, at any angle you will have similar circle. Now semicircle, again center of semicircle will be this. That is, with this center you are able to create semicircle using compasses. So order of rotation, it is very interesting. It will be only 1. Why? Consider this is a point. You are rotating it. When you reach complete 180 degrees, then you will have this semicircle downwards, which will not be very similar to this one. Therefore, you have to again rotate it because this point is now here. You are rotating and it will come back. So any object, has at least 1 order of rotational symmetry, therefore 1 for semicircle. And what is the angle? Complete 360. For any object which has only single order of rotation symmetry will have angle of rotation as 360 degrees. As humans, we have angle of rotation as 360 degrees and we have order of rotation as 1. So that is your 4th. Question 5. Name the quadrilaterals which have both line and rotational symmetry of order more than 1. The answer of this question can be given with the help of previous question. So we have considered square, rectangle and rhombus. Well, these 3 figures, square, rectangle and rhombus, have order of rotational symmetries more than 1, and we have discussed and we have shown here as well that it is more than 1. Also, they have line symmetry more than 1 because square has 4 line of symmetry, 1, 2 and 2 with diagonals making 4. Rectangles has these line of symmetry. Remember, they don't have diagonals as line of symmetry. And at last, rhombus has 2 line of symmetries, 1 and 2, and it has 2 rotational symmetry as we have discussed in previous question. So it is not only square, but we have square, rectangle and rhombus. Also the question was saying name the quadrilaterals, not only quadrilateral. That is a 5th. Question 6th. After rotating by 60 degrees about a center, a figure looks exactly the same as its original position. At what other angles will this happen for the figure? This question focuses about angle of rotation in case of order of rotational symmetry. So it is saying that after rotating by 60 degrees about the center, a figure looks exactly the same as its original position. So whenever we see 60 degrees, then hexagon strikes in our mind because it has 60 degrees as angle of rotation. Why? Because angle at a point is 360 degrees. It has 6 sides, therefore 360 over 6 is 60 degrees. So the hexagon has order of rotational symmetry as 6 because it can be rotated 6 times to cover itself exactly. Now the question is saying, at what other angles will this happen for the figure? Well, we have to just study the multiplication table of 60, that is 6, and we will fix 0 in the last. Now how we do it practically? We will copy the hexagon onto a tracing paper, this one, and we will put a yellow dot or any colored dot for that matter. Using the yellow dot as the starting point, we will rotate the hexagon until it covers itself exactly. So first of all, you will make this hexagon on a paper, and you will make another hexagon and put a needle here or a pin here, and you will rotate it, and we will rotate it until we make a complete circle, that is we will rotate it 360 degrees, and we will see the number of times that above hexagon matches perfectly on this hexagon. So let's visualize the rotations. So this is your starting point of the copied hexagon. We rotated it once, that is 60 degrees, and question was also saying after 60 degrees. So we see this image very similar to this image, that is this hexagon covered this hexagon completely, and 60 degrees turn has been done and it is rotated once. Now we will rotate it twice until this figure completely covers this figure, and we will see that we have to rotate it with another 60 degrees, therefore total from starting point it will be 120 degrees. So this question is not asking just 60 degrees each time, it is saying that by how much angle we are rotating an object from the initial point. So each time we have to take this as initial point for a degree measure, and third time that will be a straight line because this point will be here, so we will rotate it 180 degrees from initial point because it is a straight line. Then addition again with 60 degrees, this point comes here, so addition of another 60 makes 240 degrees. Now rotated fifth time, this angle will be 300 degrees, that is addition of 60 to 240. Now the last time, and we get it back where we started, that is the sixth turn, therefore 360 degrees total rotation has been done. We have just found it by addition of 60 or multiplication table of 60. 60 into 2 120, 3s are 180, 4s are 240, and so on, and 6 are 360 degrees. So that is your sixth. Seventh, can we have a rotational symmetry of order more than 1 whose angle of rotation is first 45 degrees, second 17 degrees? Number first, if we consider 45 degrees, well, we have studied numerous figures that have 45 degrees and they have rotational symmetries. One of the figure is octagon, so it has 8 sides. When you divide 360 over 8, you get 45 degrees. So we have to rotate it 45 degrees. So the answer is yes, because 360 over 45 equals 8. Therefore, total 8 orders of rotational symmetry may be obtained as in case of octagon. That was first. And for 17 degrees, well, no, because 17 is not exactly divisible by 360. It's simple. If a number is exactly divisible with 360, or when we multiply a certain exact number to any given number and it gives you 360 degrees, then only your rotational symmetry is possible. Because what we are doing in rotational symmetry is we are just rotating it along any fixed point. So angle at any fixed point, that is complete angle, is 360 degrees, and if any given angle is a multiple or exactly divisible with 360, then only it can have rotational symmetry of order more than 1. Else, every object in this universe will have at least 1 order of symmetry. So that is your second part, and that completes your last question, question 7th.